Hello, dear traveler of the cosmos. Where are you right now? In what corner of the world does your consciousness rest as these words flow to you? What time is it there? Is it night, and can you see the stars through your window? Or perhaps it's morning, and the light of the sun, our nearest star, is bathing your face with its warm presence. No matter the moment, no matter the place. What matters is that you're here with me, ready to embark on a journey that will take us to the edges of the universe and into the depths of time. How do you feel? Relaxed? Curious? Maybe a little drowsy? Perfect. Let yourself be carried by this sense of tranquility. Because today we're going to explore one of the most beautiful and contemplative mysteries of the cosmos. Have you ever stopped to think about silence? Not the silence of your room, perhaps interrupted by the tick-tock of a clock or the distant murmur of daily life. I'm talking about deep, absolute, cosmic silence. The silence that permeates the vacuum between stars, that witnesses the births and deaths of entire worlds without emitting a single sound. It's about this silence that we're going to talk today. More specifically, about how some of the most magnificent creatures in the universe, the stars, can die in absolute silence, without fanfare, without spectacular explosions, just dying away. Like a candle that gently extinguishes in the night breeze. Have you ever thought about this? That not all deaths in the universe are violent? That there are stars that, after billions of years illuminating the cosmos, simply whisper a silent goodbye and transform into something completely different? This is the story of those discrete stars, those suns that choose silence for their final departure. It's a story of transformation, of deep time, of melancholic beauty. It's a story that speaks to us about ourselves, about the nature of existence, and about what it really means to depart in a universe where nothing truly disappears, only transforms. Close your eyes for a moment. Take a deep breath. Feel the air entering your lungs, oxygen that was forged in the cores of ancestral stars, carbon that danced through nuclear reactions for millions of years before reaching you. Each breath you take is a cosmic communion, an intimate connection with the history of the universe. Now imagine the vacuum of space, where there's no air, where there's no sound, where stars shine in eternal silence. Imagine the vastness between galaxies, where light travels for billions of years without encountering anything but emptiness. It's in this silence that our story unfolds. The universe, is not a noisy place. Despite all the cosmic explosions, all the galactic collisions, all the violent births of stars, the cosmos is fundamentally a place of profound silence. And it's precisely in this silence that some of the most beautiful transformations happen. Ready to begin? Then let's embark together on this journey through time and space, exploring the secrets of stars that chose whispers instead of screams, contemplation instead of violence, silent eternity instead of momentary glory. Not all stars are born equal. Some come into the world as furious giants, others as luminous whispers. It's about the latter that I want to talk to you now, the small stars, the discrete ones, those that science calls low-mass stars. Have you ever held a grain of sand? Feel how small it is between your fingers, almost insignificant? Now imagine that this grain of sand was, in fact, a star. A star that, despite its modest size, manages to shine consistently and serenely for trillions of years. Trillions. A number so vast that our human minds can barely comprehend it. Let's do an exercise together. Try counting to 1,000. If you count one number per second without stopping, it will take approximately 17 minutes. Now imagine counting to 1,000,000. It would take almost 12 continuous days. 1,000,000,000, more than 31 years. 1,000,000,000,000. More than 31,000 years. And we're talking about stars that can live for 10 trillions of years or more. Our sun, which seems so grand and powerful to us, is actually one of these medium-sized stars. It has about 1.989 kilograms of mass, an impressive number, but one that places it in the category of common stars. To visualize this mass, imagine that each kilogram was a grain of sand. You would need more beaches than exist on the entire Earth to represent the sun's mass. There are stars much larger than it, true cosmic monsters that live short lives and die in spectacular explosions. Imagine stars with 50, 100, even 300 times the sun's mass. They're like cosmic fireworks, bright, spectacular, but ephemeral. But there are also smaller stars, much smaller ones, that follow a completely different path. Think of a red dwarf star. It has only 10% to 50% of our sun's mass. It might seem like little, but this apparently small difference determines a completely different destiny. It's as if the universe whispered to these smaller stars, "You will have a long life, very long, but also very quiet." Have you ever wondered why some people speak softly and others shout? Stars work similarly. Larger stars shout. They burn their nuclear fuel quickly, live intensely, die young in grandiose explosions. Smaller stars whisper. They burn their fuel slowly, live incredibly long lives, and when they reach the end, they simply fade away. The secret lies in pressure. Imagine you're squeezing a wet sponge. If you squeeze too hard, all the water comes out at once, in violent jets. If you squeeze gently, the water drips slowly, but for much longer. Something similar happens with stars. The greater the mass, the greater the gravitational pressure in the core, the faster the nuclear fuel is consumed. A red dwarf star can shine for 10 trillion years. 10 trillion. Our universe is only 13.8 billion years old. This means these small stars are still in the infancy of their lives. They will continue shining long after stars like our sun have departed long ago. Imagine this. When the universe was young, just a few million years after the Big Bang, the first red dwarf stars began to shine. They're still there, still shining, still whispering their light through the cosmos. They witnessed the formation of the first galaxies, the birth and death of billions of other stars, the evolution of life on countless worlds. They are the librarians of the cosmos, silent, patient, preserving the memory of epochs that only they remember. And the most fascinating part? Many of them haven't even reached the middle age of their lives. But how do they die? There lies the beauty of cosmic silence. When a red dwarf finally reaches the end of its nuclear life, there's no explosion, no violence. There's only a subtle transformation, a transition so smooth it's almost like watching a metamorphosis in extremely slow motion. Let's pause for a moment, take a deep breath. Feel your heart beating in your chest. Each beat is powered by energy that comes, ultimately, from the sun, and the sun's energy comes from an extraordinary process that happens in its core, nuclear fusion. Imagine 4 friends meeting at a cosmic party. They arrive separately, each with their own energy, their own characteristics. These friends are protons, hydrogen nuclei, the simplest and most abundant particles in the universe. But something magical happens when they meet in the core of a star. They embrace so intensely that they become a single entity, lighter than the sum of the 4 originals. This cosmic embrace isn't easy. Protons are like very shy people who naturally repel each other. They carry positive electric charge and like charges repel. It's like trying to force 2 magnets of the same pole to touch. They resist vigorously. But in the core of a star, conditions are extreme. Temperature reaches millions of degrees. Pressure is billions of times greater than Earth's atmospheric pressure. Under these conditions, protons move so rapidly that they can overcome their natural repulsion and fuse. When 4 protons finally embrace and become a helium nucleus, something extraordinary happens. The total mass of the helium is slightly less than the sum of the masses of the 4 original protons. Where did this lost mass go? It transformed into pure energy, following Einstein's famous equation, E equals mc. It's a minuscule amount of mass that's lost. Only 0.7% of the original mass. But when you multiply this small difference by the speed of light squared, an astronomical number, the result is a formidable amount of energy. To visualize this, imagine you could completely convert a grain of rice into pure energy. That energy would be sufficient to power an entire city for several hours. This is how nuclear fusion works. Small losses of mass translate into enormous releases of energy. In the sun, this process happens trillions of times per second. Every second, the sun converts approximately 600 million tons of hydrogen into helium, releasing energy equivalent to the explosion of 100 billion hydrogen bombs. And even so, this is only a minuscule fraction of the sun's total mass. Have you ever watched a drop of water sliding very slowly down glass? In smaller stars, nuclear fusion happens at a similar pace, slowly, smoothly, without hurry. It's as if the universe had all the time in the world. And, in fact, it does. In the core of a red dwarf star, the temperature is only about 3 million degrees Celsius. Compare this to larger stars, where temperature can reach 100 million degrees. It's the difference between a tranquil campfire and an industrial blast furnace. Both produce heat, but the intensity and duration are completely different. This temperature difference translates into a dramatic difference in fusion speed. In smaller stars, the process is so slow that they can maintain this delicate balance for trillions of years. It's like having a candle that burns so slowly it lasts almost an eternity. Nuclear fusion in a red dwarf is a perfect example of cosmic efficiency. These stars extract energy from practically all the hydrogen in their interior, not just from the central core. It's as if they had learned to use every drop of available fuel. Imagine a car that could extract energy not just from the gasoline in its tank, but from every hydrocarbon molecule in the entire vehicle. That car could run for millions of miles with a single full tank. That's how red dwarfs work. They are cosmic energy efficiency machines. But you might be wondering, and when this fuel runs out? That's a fascinating question. And the answer leads us to one of the most silent and elegant transformations in the universe. When a small star finally exhausts its nuclear hydrogen, it doesn't explode. It doesn't scream. It just dies. It's as if, after trillions of years of quiet life, it simply decided it's time to transform into something new. Have you ever wondered how something so gigantic can sigh? That's where the true cosmic poetry begins. Even the most silent stars have their moments of dramatic transformation. Imagine a ballerina who, after years of smooth and elegant performances, decides to make one last performance, not extravagant but deeply touching. This is how low-mass stars behave when they begin to feel the weight of cosmic age. When the hydrogen in the core of a small star finally runs out, something extraordinary happens. It's as if the star, which maintained perfect balance for trillions of years, suddenly lost its emotional center of gravity. The core, now composed mainly of helium, begins to contract under its own weight. Have you ever squeezed a tennis ball? Notice how it offers resistance, but after a certain point it can't compress anymore. Something similar happens with the stellar core, but on an incomprehensible scale. This core, now denser, generates heat, not through fusion, but through gravitational contraction. It's as if the star were warming its hands by rubbing them rapidly. This heating causes the star's outer layers to expand dramatically. It's a fascinating cosmic paradox. The center contracts and heats up, but the periphery expands and cools. The star becomes much larger, cooler on the surface, but denser in the center. Thus is born what we call a red giant. But don't be fooled by the name giant. When we talk about small stars becoming red giants, we're not talking about something spectacular like the explosions of large stars. It's more like watching a flower blooming in extremely slow motion, beautiful, gradual, almost meditative. Imagine watching a rose opening, but instead of happening in a few days, the process took millions of years. Each petal unfolding with impossible slowness, revealing layers of beauty that can only be appreciated through cosmic patience. The process of transformation into a red giant is so subtle that, if you could observe one of these stars for a few million years, you would see something like cosmic breathing. The star expands smoothly, its light becomes more reddish, its surface temperature decreases. It's as if it were preparing for a long nap. During this phase, something simultaneously magical and melancholic can happen. If the star has planets, they can be gently embraced by the stellar expansion. It's a silent death for these worlds too, not a violent annihilation by a supernova, but a gradual and almost loving integration with their star mother. Imagine a world where life perhaps once flourished, where blue oceans reflected their star's light, where wind blew through alien forests. As the star slowly expands, this world gradually heats up. First, the oceans evaporate. Then the atmosphere dissipates. Finally, the rock itself melts and integrates into the expanded star. It's a form of melancholic immortality. Atoms that once formed mountains and seas become part of a larger cosmic dance, glowing softly in the expanded atmosphere of the red giant. Have you ever thought about this? What kind of cosmic poetry exists in the idea of a world being slowly embraced by its star? It's almost as if the universe whispered, "Nothing is lost, everything transforms." All separation is temporary. The red giant phase can last hundreds of millions of years for stars like the Sun. But for very small stars, the process is even more prolonged and smooth. It's as if these smaller stars had learned the art of gradual transformation, of change without violence. During this phase, the red giant pulses gently, like a cosmic heart beating in slow motion. Its outer layers expand and contract rhythmically, creating waves of light that propagate through space. It's visual music, a symphony of light and movement that can be detected by sensitive telescopes. But the red giant is only a transitional phase, a poetic interlude in the star's life. The true silence, the true transformation, is still to come. It's when these outer layers finally detach that we witness one of the most subtle and beautiful spectacles in the universe. Now we arrive at the most delicate moment of our cosmic journey. Imagine you're sitting in a very old library where the only sound is the whispering turn of pages yellowed by time. It's in this type of reverent silence that small stars make their final transition. The red giant phase doesn't last forever. Eventually, the star reaches a critical point where it needs to make a fundamental cosmic decision. Will it explode like a supernova, sending shock waves through interstellar space? Or will it choose a more discreet, more contemplative path? For low-mass stars, the choice is already predetermined by physics itself. They simply don't have enough mass for the spectacular violence of a supernova. It's as if the universe whispered to them, "You've already given so much light and heat to the cosmos. Now you can rest in peace." What happens next is almost poetic in its delicacy. The star's outer layers, now expanded and tenuous like cosmic mist, begin to detach slowly. It's not an explosion, it's more like a very long and deep exhalation. Imagine someone releasing a sigh that extends for thousands of years, each particle of air carrying memories of a lifetime. This cosmic exhalation forms what astronomers call a planetary nebula. The name is a bit misleading. It has nothing to do with planets. It's just a historical accident from when the first telescopes made these nebulae look like planetary disks. In reality, they are gas bubbles that expand gently through space, illuminated by the light of what remains of the star in the center. Have you ever seen soap bubbles floating in the air on a sunny day? Observe how they are delicate, translucent, almost ethereal, with iridescent colors dancing on their surfaces. A planetary nebula is the cosmic version of these bubbles, a gaseous work of art that expands in silence through the vacuum of space. Imagine layers of different gases: hydrogen, helium, oxygen, carbon, each glowing in its own characteristic color when illuminated by the ultraviolet radiation of the central star. Hydrogen glows red, oxygen in green and blue, nitrogen in shades of red and orange. It's as if the star were painting its autobiography in the sky, each color representing a different chapter of its life. These nebulae can extend for light years in diameter, creating structures of indescribable beauty. Some look like cosmic rings, others resemble galactic butterflies, and still others remind us of giant eyes observing the universe. Each one is unique, like a cosmic fingerprint of the star that created it. The process of forming a planetary nebula can take tens of thousands of years. It's like watching a giant flower blooming in extremely slow motion, its gaseous petals unfurling slowly against the starry backdrop. But what happens to the star's heart? There lies the true mystery and the true beauty. When all the outer layers dissipate like cosmic smoke, what remains is something extraordinary, a white dwarf. It's as if, after a lifetime of frantic nuclear activity, the star finally decided to sit in a cosmic rocking chair and simply exist. There's no more nuclear fusion happening. No more energy being actively generated in the core. Just a small object, incredibly dense, that glows softly with the residual heat of trillions of years of active life. A white dwarf is so dense that a teaspoon of its material would weigh as much as an elephant. Imagine all the mass of a star compressed into an object approximately the size of Earth, its matter compacted to the extreme but in perfect peace with itself. And then begins the longest and quietest wait in the universe, the slow cooling that can last longer than the current universe has existed. Have you ever stayed awake very late at night, just contemplating the ceiling, lost in deep thoughts about life, the universe, and your place in it? There's something profoundly meditative about that experience, the feeling that time stretches infinitely. that you're suspended in an eternal moment of contemplation. This is how we should imagine the existence of a newly formed white dwarf. A white dwarf is like a still glowing ember from a fire that recently extinguished. It shines not because it's producing new energy through nuclear fusion, but because it still retains the heat accumulated from its previous life, like a stone that was exposed to the sun all day and continues warm late into the night. It's an object approximately the size of Earth, but with the mass of an entire star compacted into this small volume. To visualize this extreme density, imagine trying to compress the entire population of Earth into a single room. Now multiply that compression by trillions of times. This is how dense and compact the interior of a white dwarf is. Imagine trying to compress the entire sun down to the size of our planet. The result would be something so dense that the atoms themselves would be forced to reorganize in completely new and exotic ways. Electrons would be squeezed against atomic nuclei, creating a type of matter that only exists under these extreme conditions, a matter where quantum laws dominate on a macroscopic scale. But here's the most fascinating aspect of white dwarfs. They have absolutely no hurry at all. It's as if the universe had all the patience in the world to watch this slow and gradual cooling process. Have you ever watched a hot cup of coffee slowly cooling? In the first minutes, heat dissipates quickly. You can feel the steam rising, the temperature noticeably decreasing. Then the process becomes slower, more gradual. A white dwarf works similarly, but on a time scale that completely defies our human understanding. In the first millions of years after its formation, a white dwarf loses heat relatively quickly, relatively being a very relative term when we talk about cosmic scales. Its surface, initially white and bright like a high-temperature star, begins to cool and become yellowish. It's like watching the sunset in extremely slow motion. White transforms to yellow, then to orange, then to red, each transition taking millions or billions of years. But even after billions of years of cooling, the white dwarf still maintains considerable temperature. Its surface may be at only a few thousand degrees, cold by stellar standards, but still incandescent by terrestrial standards. It's as if it had such a vast heat reservoir that it could warm entire civilizations for unimaginable periods. Scientists calculate that a typical white dwarf can take more than 10 trillion years to cool completely. To put this in perspective that our human minds can at least try to comprehend, our universe is only 13.8 billion years old, less than 1.4% of the time necessary for a white dwarf to cool completely. This means that not even the oldest white dwarfs in the universe, those formed when the cosmos was still young, have had enough time to cool completely. They're still in the initial phase of their long cooling process, like cosmic wines that are still maturing in their space cellars. It's a form of silent immortality almost incomprehensible. These dead stars continue glowing softly like cosmic candles that obstinately refuse to extinguish. They are silent witnesses to the universe's evolution, crystallized memories of stars that once warmed distant worlds. Imagine a white dwarf as a cosmic library where the entire history of its progenitor, star, is written in the crystalline structure of its matter. The heavy elements in its core are like chapters of a book, telling about the billions of years of nuclear fusion that created them. Oxygen speaks about the reactions that happened when the star was burning helium. Carbon tells about the final stages of active stellar life. During the long cooling process, the white dwarf gradually crystallizes, transforming into something like a giant cosmic diamond. It's not a poetic metaphor, it's literally what happens. The carbon and oxygen in the white dwarf's interior organize into ordered crystalline structures, creating the largest crystal in the universe. Have you ever wondered why the universe created these creatures so persistent, so patient? Maybe it's its natural way of ensuring that some precious things are never completely forgotten, that some fundamental memories persist beyond any time measure we can imagine or comprehend. White dwarfs show us that deep time is not an enemy to be defeated or a limitation to be overcome, but rather a patient ally, a gentle sculptor, a silent preserver that works on scales that transcend any human urgency. Now let's enter an almost mystical territory of science, the distant future of the universe. so remote that our current universe would seem like just a brief initial blink in its long and epic history. Imagine you could travel through time, not to the past, but to a future so absurdly distant that our current universe would appear, in comparison, like the first seconds of a very long day. In this almost incomprehensible future, white dwarfs will have finally cooled completely. They will become what scientists call black dwarfs, objects that emit no light of their own, completely cold, invisible against the absolute darkness of space. They are elegant cosmic ghosts, crystallized and preserved memories of a cosmic golden age, when the universe was young, hot, and incredibly luminous. It's a concept almost poetic in its melancholy, stars that became cosmic ghosts, present but invisible, reminding us that not everything that exists can be seen or detected. It's as if the universe had developed a form of material nostalgia, preserving the memories of its luminous youth in silent and invisible objects. Have you ever walked in a dense forest during a moonless night when clouds cover even the stars? Do you know that strange feeling of knowing that trees are there around you, even though you can't see them? You can sense their presence, imagine their shapes, almost touch them with senses that don't depend on sight. In a universe dominated by black dwarfs, the situation would be cosmically similar. Trillions of these objects would be floating silently through space, invisible to the most powerful telescopes, but still exerting their subtle gravitational influence on the fabric of space-time. They would be like invisible footprints of cosmic giants, marks left by stars that once illuminated entire galaxies. These black dwarfs would be like cosmic libraries sealed forever. Each one would contain, in its perfectly ordered crystalline structure, the complete memories of a star that once shone gloriously. The carbon and oxygen in their cores would be like pages of an eternal cosmic book, telling the story of trillions of years of nuclear fusion, of heated planets, of possible civilizations that perhaps flourished under their light. Imagine being able to hold one of these objects in your hands, if that were physically possible. You would be holding the concentrated history of billions of years of stellar evolution, the entire biography of a star compressed into a form so dense that its very molecules would behave in ways that defy our everyday understanding of matter. But here's something even more fascinating and almost incomprehensible. Theoretically, these black dwarfs would not be the absolute end of the story. Even in the absolute cold of space, even in the total darkness of an aged universe, extremely slow quantum processes would still be occurring silently. Over periods of time almost incomprehensible, we're talking about 10, 1,500 years or more, these black dwarfs could eventually disintegrate through exotic quantum processes. It's as if the universe had infinite patience, willing to wait for periods of time so vast that our human language doesn't have adequate words to describe them. To try to understand the magnitude of these temporal numbers, imagine that each second that has passed since the Big Bang was represented by a grain of sand. You would need more universes than particles exist in the current cosmos just to have enough sand to represent the time necessary for a black dwarf to quantum disintegrate. It's on this absolutely mind-boggling timescale that black dwarfs would eventually whisper their final goodbye to the universe. Not through explosions or collapses, but through the most silent quantum decay imaginable, proton by proton, particle by particle, disappearing into the fundamental quantum structure of space-time. But until then, and until then is an expression that doesn't do justice to the temporal vastness involved. They will remain as silent monuments to stars that once illuminated the cosmos. They will be invisible reminders that not all greatness needs to be seen to be real, that some of the universe's deepest creations exist in the frequencies of absolute silence. And what if the universe were slightly different? What if fundamental physics had slightly altered constants? Maybe black dwarfs would be truly eternal, floating forever in a dark and silent cosmos, eternal guardians of memories that would never fade. It's a perspective that invites us to reflect deeply on the nature of permanence and impermanence, on what it really means to last in a universe in constant and slow transformation. Does eternity really exist? Or is it just a matter of timescales so vast they become indistinguishable from eternity for beings like us? Black dwarfs teach us that even the concept of forever can have nuances that our human minds can barely glimpse. They are the materialization of deep time, the embodiment of cosmic patience taken to its absolute extreme. Let's pause our journey through cosmic time and delve into the fundamental physics that governs these silent deaths. It's as if we were carefully opening the mechanism of a cosmic clock to understand how its most delicate gears work in perfect harmony. The difference between a silent stellar death and an explosive one comes down fundamentally to stellar mass. It's an elegant concept in its mathematical simplicity. Mass determines destiny. There's no choice, no variation. It's a physical law as immutable as the gravity that keeps us bound to Earth. Imagine two people walking toward the same steep hill. One carries a light backpack containing only the essentials for the journey. The other carries a heavy backpack overloaded with unnecessary provisions. Both can reach the top, but their journeys will be completely different in pace, effort, and consequences. The person with the light backpack can climb tranquilly, stopping to contemplate the landscape, observing the details of the path, maybe even choosing alternative, more interesting routes. The person with the heavy backpack needs to use all their concentrated energy just to keep climbing, panting, sweating, forced to take the most direct and efficient path. With stars, the backpack is precisely the total mass. Stars with more mass exert a proportionally more intense gravitational force on themselves. It's as if they were constantly squeezing their own cores with increasingly tremendous force as they accumulate mass. This intense gravitational pressure dramatically accelerates nuclear fusion processes. It's the fundamental difference between a carefully controlled campfire by an experienced camper and an uncontrolled forest fire. Both involve the same basic combustion processes, but the intensity, speed, and duration are completely different. Stars with more than 8 times the Sun's mass are like uncontrolled nuclear furnaces. They burn their nuclear fuel so voraciously that, in just a few million years, a blink of an eye on the cosmic time scale, they've already exhausted their energy reserves. It's like a compulsive spender who exhausts their entire inheritance at an extravagant party. When this happens, the resulting gravitational collapse is so violent and sudden that it results in a supernova, an explosion so energetic that it can briefly outshine an entire galaxy, being visible billions of light years away. But stars with less than 8 solar masses are like very well-controlled fires by master craftsmen. They learn the cosmic secret of moderation, burning slowly with maximum efficiency, maintaining an almost miraculous balance between two titanic forces, the gravitational pressure that tries to compress them to collapse and the nuclear radiation, pressure that tries to expand them to dispersion. It's as if these smaller stars had instinctively discovered the secret of cosmic longevity. It's not about shining with maximum possible intensity, but about shining consistently, sustainably, for periods of time that transcend any human concept of duration. Have you ever observed a high-quality candle burning slowly? Notice how the flame finds a perfect and stable balance. It doesn't grow uncontrollably nor extinguish easily. It simply persists, consuming the wax in a constant and absolutely predictable manner. Low-mass stars are exactly the cosmic candles of the universe. When these stars finally reach the inevitable end of their active nuclear life, they don't have enough mass for the violent collapse that characterizes a supernova. Instead, they go through a process that physicists poetically describe as gentle degenerative collapse, a gradual transition to a completely new and exotic state of matter. It's almost poetic in the language of physics. Instead of a violent and destructive implosion, we have a smooth and gradual transition to a state of matter that obeys quantum laws on a macroscopic scale. Electrons in the star's core become degenerate, a technical term from quantum mechanics that describes a state where particles are forced by the fundamental laws of physics to occupy the lowest possible energy levels. Imagine an elegant theater where all the main floor seats are completely occupied, and people who arrive later have to necessarily sit in the upper balconies, following a rigid order determined by the establishment's rules. This is exactly how electrons behave in a white dwarf. They are forced by quantum laws to occupy the lowest available energy seats, creating an exotic form of matter that can only exist under these extreme conditions. This degenerate matter is precisely what gives white dwarfs their impressive stability. It's as if quantum mechanics itself provided a perfectly adequate cosmic chair. where these dead stars can sit comfortably and rest for trillions of years without disturbance. Electron degeneracy pressure acts as a quantum structural support, resisting additional gravitational collapse and allowing the white dwarf to maintain its approximately constant size while slowly cooling through cosmic eras. Each white dwarf floating silently through the cosmos is like an encapsulated time machine, carrying in its dense crystalline structure the chemical and physical memories of cosmic apex long forgotten. Imagine being able to hold in your hands, if this were physically possible, an object that existed when the universe was young and impetuous, when the first galaxies were still forming like whirlpools of baby stars. This is exactly what a white dwarf represents in scientific and poetic terms: a crystallized cosmic archive, a library of stellar memories preserved in solid form. Have you ever carefully examined the concentric rings of a very old tree that was cut down? Each ring meticulously tells the story of a specific year in the tree's life, whether it was a year of abundant rain or severe drought, whether it was rigorously cold or excessively hot, whether there were forest fires or periods of peace. White dwarfs work in a conceptually similar way, but operating on a timescale trillions of times vaster and more comprehensive. The complex chemical composition of a white dwarf reveals in detail the complete history of its progenitor star. The heavy elements stratified in layers in its core are like unique and indelible chemical signatures, telling us about the specific conditions that existed when the star was in its active phase of nuclear fusion. It's as if each white dwarf were a meticulously preserved cosmic time capsule, guarding precious information about universal epoch never personally visit, but that we can study through these natural stellar archives. Modern scientists can study these dead stars using advanced spectroscopy and sophisticated astronomical analysis techniques, patiently reconstructing the history of the primitive universe's chemical evolution. It's literally like doing cosmic archaeology, excavating through temporal layers using telescopes instead of shovels, discovering chemical artifacts instead of ancient pottery. Some white dwarfs are so incredibly ancient that they formed when the universe had only a few billion years. They are contemporaries of the first true galaxies, silent witnesses to fundamental cosmic events that shaped the cosmos as we know and observe it today. Imagine being one of these ancestral white dwarfs, carrying memories of 10 billion years. You would have silently watched the birth and death of millions of other stars around you. You would have observed entire galaxies forming, evolving, colliding, and transforming. You would have witnessed the birth of rocky planets, the formation of complex solar systems, the possible emergence and extinction of entire civilizations. And all of this in absolute silence, just existing, observing, preserving memories in your increasingly crystallized internal structure. It's a form of almost Shakespearean melancholic immortality. These dead stars are like solitary cosmic librarians, religiously guarding all the accumulated knowledge of the universe in their crystalline physical structures, but with no one to read their stories, no visitors to consult their infinite archives. Have you ever thought deeply about this? That the universe may be literally full of silent memories, of fascinating stories told in chemical and physical languages that we're only beginning to learn to adequately decipher? There's something profoundly touching and almost romantic in the idea that each white dwarf represents a complete but unwritten cosmic biography, an entire stellar life summarized and preserved in a small dense object that glows softly and patiently in the seemingly empty darkness of interstellar space. And when we contemplate the fact that, in a distant cosmic future, these same white dwarfs will become completely invisible black dwarfs to the naked eye in conventional telescopes, the metaphor becomes even more poetic and touching. They will become invisible memories, stories that continue to exist physically but can no longer be easily seen or detected, knowledge that stubbornly persists even when no one is present or available to directly witness it. It's as if the universe had developed a sophisticated form of material nostalgia, preserving its most precious memories and objects that become progressively more silent and invisible with the passing of cosmic eras, but that never really disappear completely. Each white dwarf is a unique window to the cosmic past, a preserved fragment of epochs that would otherwise be completely lost forever. They connect us directly with the ancestral history of the universe, allowing us to touch, even if indirectly, the first chapters of the cosmic epic that is still being written. There's something profoundly paradoxical and philosophically intriguing about the silent death of stars. How can something so cosmically fundamental, the definitive end of a star that shone for billions or trillions of years, be so discreet, so unpretentious, so undramatic? It's as if the universe had developed a sophisticated way of dying that is, simultaneously, an absolute end and a completely new beginning. Think carefully about this. When a small star gracefully transforms into a white dwarf, it doesn't disappear from the universe as if it had never existed. On the contrary, it condenses, concentrates, becomes exponentially denser and, in a very real sense, more essential. It's as if death were, paradoxically, a form of maximum concentration of the life that came before. Have you ever carefully observed how expensive perfume behaves when applied? When you initially apply it, it spreads quickly, occupies a larger olfactory space, announces its presence almost exuberantly. But as hours pass, it concentrates, becomes more subtle, more refined, more essential, and curiously, more lasting and memorable. Silent stellar death works in a conceptually similar way. The star becomes drastically more concentrated, more essential, purer in its final form. All the hydrogen it burned, all the helium it produced, all the heavier elements it forged in its core during its active life, all of this condenses into a perfect crystalline form. A white dwarf literally contains the entire detailed chemical history of its progenitor star, compacted into an object approximately the size of a terrestrial planet. It's as if the star's entire life, each nuclear reaction, each moment of balance between gravity and radiation pressure, were distilled and preserved in its purest and most concentrated essence. But here's the central paradox that makes us reflect on the nature of cosmic communication. By becoming more concentrated and essential, the star also simultaneously becomes more silent. It's as if there were a fundamental law of the universe that whispers, the more essential and refined you become, the less you need to shout to be noticed. This invites us to a deep reflection on the nature of communication in the vast universe. Larger stars shout their death through spectacular supernovas that can be observed and detected from distant galaxies, billions of light years away. Their deaths are announced throughout the cosmos like cosmic fireworks, impossible to ignore. But smaller stars whisper their final transformation, creating silent objects that can persist and communicate their presence in subtle ways for periods of time almost infinite, well beyond the duration of any spectacular explosion. Which form of cosmic communication is more effective in the long term? The one that is immediately heard and noticed by the entire observable universe, or the one that persists whispering patiently for trillions of years, available to whoever is willing to pay careful attention? It's like comparing a loud shout in a crowded stadium with an intimate whisper in a silent library. The shout is instantly heard by tens of thousands of people, but quickly dissipates in the air and is forgotten. The whisper can only be heard by those paying close and careful attention, but can continue echoing in memory and influencing thoughts for much, much longer. Perhaps the universe, in its emergent wisdom, developed these two fundamentally different stellar death strategies to serve different complementary cosmic needs. Supernovas function as cosmic newspapers. They spread information quickly across vast spatial distances, announcing important events, distributing newly forged heavy elements to future generations of stars. Silent deaths, on the other hand, function as specialized cosmic libraries. They preserve detailed information for vast periods of time, maintaining precise records available for future investigation, guarding memories that would otherwise be completely lost. Have you ever sincerely wondered which of these cosmic strategies is more important for the long-term evolution of the universe? The rapid and spectacular dissemination of elements and energy, or the patient and silent preservation of information and memory? The profound answer may be that both strategies are equally important and complementary. The universe simultaneously needs its spectacular cosmic journalists and its silent librarians. It needs both its loud voices that announce dramatic changes and its eternal whispers that preserve continuity through eras. And we, as conscious and curious observers of this extraordinary cosmos, have the unique and privileged opportunity to appreciate and study both forms of cosmic poetry. We can marvel at the spectacular violence and dramatic beauty of supernovas, but we can also be profoundly moved by the silent melancholy and persistence of white dwarfs. Silence, is fundamentally a language, not a language composed of audible words or detectable sounds, but a much deeper and subtler language made of pure presence, of concentrated existence, of meaning that transcends the need for vocal or sonic expression. And in the immense and mainly silent cosmos, white dwarfs emerge as the true eloquent masters of this universal silent language. Have you ever experienced being in a place so profoundly silent that you could actually hear the silence itself? Perhaps in a very old historical library where centuries of human knowledge rest in respectful silence, or in a primordial forest covered with fresh snow where every sound is muffled by white purity, or in a very quiet dawn when the entire world seems suspended in a moment of absolute peace. There's something almost tangible about this type of deep silence. It's not simply the mechanical absence of sound, but a positive presence in itself, an almost palpable force that can be felt, breathed, experienced in ways that transcend our usual senses. This is exactly how we should imagine and understand the cosmic silence of white dwarfs. They're not simply not making noise passively, they're actively communicating through their concentrated quietude, through their dense and meaningful presence. Their silent language is composed of sophisticated physical elements, extreme material density, subtle but measurable gravitational fields, residual heat that gradually diminishes, chemical compositions that tell complete stories, and gravitational influences that delicately curve the very fabric of space-time around them. Imagine trying to communicate exclusively through your physical presence, without words, without obvious gestures, without sounds, just existing with intensity and meaning. It's a profoundly intimate and sophisticated form of communication. You need to be very close, very attentive, very sensitive to perceive and interpret the subtle nuances of this silent language. Modern astronomers have patiently learned to hear and interpret this silent cosmic language. They meticulously observe how light from distant stars curves in specific ways when passing near a white dwarf, detect the extremely subtle gravitational waves that these dense objects create when orbiting each other in pairs, carefully analyze the complete spectrum of light they emit to decipher their detailed chemical composition and thermal history. It's literally like learning to read cosmic lips, to interpret whispers that have traveled through light years of apparently empty space, carrying messages encoded in frequencies that require extremely sensitive instruments to be detected and decoded. Each white dwarf tells its unique story in a slightly different way from the others. Some are hotter, others cooler. Some are composed mainly of crystallized carbon and oxygen. Others contain more exotic elements like magnesium or neon. Some pulse softly in detectable rhythms, others remain in apparently absolute silence for astronomical periods. It's a rich and complex silent diversity, like a cosmic symphony played in frequencies that only very sensitive and sophisticated scientific instruments can detect and adequately interpret. Have you ever seriously thought about this? That perhaps most of the meaningful communication in the universe happens in frequencies we can't directly hear, in languages we're only beginning to understand through advanced science? White dwarfs teach us a fundamental cosmic lesson. Not every important message is shouted at high frequency. Some of the deepest and most lasting communications in the universe are whispered through trillions of years, preserved in crystalline structures that function as natural cosmic hard drives, available to any future civilization that develops the technological sensitivity necessary to read them. And there's something profoundly comforting and even spiritual about this scientific discovery. In a universe that can often seem chaotic, violent, and impersonal, these natural oases of absolute tranquility exist. These cosmic monuments to contemplative silence, these physical reminders that not all greatness or importance needs to be noisy or dramatic. When we look at the night sky with our naked eyes, most of the stars we can see are relatively young and active, still burning hydrogen in their cores, still announcing their presence through visible light. But among them, invisible to our direct senses, trillions of white dwarfs exist whispering their silent stories through the cosmos. It's as if the observable universe had two distinct levels of communication operating simultaneously, the obvious and spectacular level of active stars and dramatic events, and the subtle and contemplative level of crystallized memories and accumulated silent wisdom. And we, as conscious beings capable of contemplating and scientifically studying the cosmos, have the extraordinary privilege of learning both cosmic languages. We can marvel at the dramatic spectacles and colorful explosions, but we can also be profoundly moved by the eternal whispers and silent presences. It's a form of cosmic bilingualism that expands our capacity to understand and appreciate the total richness of the universal experience. Now, I want to invite you to an even deeper reflection about time, not the mechanical time we obsessively measure with our digital clocks and calendars, but deep time, cosmic time, time that functions on scales that challenge and completely transcend our everyday human understanding. Have you ever sincerely tried to imagine 1,000,000,000 years? It's a mental exercise almost impossible for our human minds evolutionarily adapted to deal with much smaller timescales. Our species Homo sapiens has existed for only a few 100,000 years, an infinitesimal fragment of cosmic history. All recorded and documented human history covers only a few thousand years. Even the oldest civilizations we know are microscopic when compared to cosmic timescales. 1,000,000,000 years is a temporal abyss that our personal and cultural experience simply cannot adequately encompass. To try to visualize this, imagine that each year of recorded human history was represented by a single step you take walking. You would need to walk approximately from New York to Los Angeles to represent our documented history. To represent 1,000,000,000 years on the same scale, you would need to take approximately 200,000 round trips between these two cities. Now try to expand your mind to contemplate 1,000,000,000,000 years. It's 1,000 times longer than 1,000,000,000 years. It's a cosmically vast period of time that, if you tried to count from 1 to 1,000,000,000,000 without stopping, would take more than 30,000 years counting continuously one number per second, without sleeping, without eating, without stopping for even a moment. And white dwarfs? They can exist, glowing softly and gradually cooling for 10 trillion years or more. It's a form of cosmic patience that absolutely transcends any human concept of persistence, resistance, or longevity. There's something profoundly meditative and almost spiritual about trying to contemplate these astronomical timescales. It's like trying to meditate on the mathematical concept of infinity. Our mind heroically extends to its absolute limit and then must simply accept and surrender to the vastness without being able to completely understand it through reason. White dwarfs are like the eternal Zen monks of the universe. They simply exist without any hurry, without anxiety, without any compulsive need to do something productive or achieve some specific goal. They are pure presence extended through periods of time that make eternity seem like a familiar and accessible concept. Imagine the cosmic patience necessary to slowly cool for 10 trillion years. It's as if these extraordinary cosmic objects had instinctively learned the deepest secret of absolute serenity. They don't fight against the flow of time, don't try to artificially accelerate or retard the natural process. They simply are. It's a total cosmic acceptance that teaches us about the fundamental nature of peaceful existence. Have you ever patiently observed a rock being slowly sculpted by running water? Drop after drop, year after year, water patiently molds and transforms the hardest stone. White dwarfs are sculpted by time in a conceptually similar way, not by physical erosion, but by gradual thermal cooling, by slow and absolutely inevitable crystallographic transformation. It's a profound cosmic lesson about authentic patience. In a human world where everything seems to constantly accelerate, where instantaneity is compulsively valued, where impatience has become almost a cultural epidemic, white dwarfs gently remind us that some of the deepest and most significant transformations happen very, very slowly. They teach us that there's no real cosmic hurry to get to any specific place, that the journey can be infinitely more important and valuable than any imagined destination, that existence itself can be a complete and satisfying form of universal success. And when we seriously contemplate the extremely distant future of the universe, when all conventional active stars will have finally extinguished and only white dwarfs remain as solitary lights in a darkened cosmos, They will become the final and silent guardians of total cosmic memory. They will be the ones to carry the last preserved physical memories of a golden age when the universe was young, energetic, and full of active light. It's an impressive and moving cosmic responsibility to be the final crystallized memory of the universe. And they assume this monumentally important responsibility in absolute silence, without fanfare, without self-promotion, just persisting with dignity. Perhaps there's a deep personal and philosophical lesson here too for our human lives. In our existences so brief and apparently insignificant compared to cosmic scales, perhaps we can learn something fundamental and transformative from the absolute patience of white dwarfs. Perhaps we can find genuine value in silent persistence, in constant and stable presence, in the capacity to exist fully without always needing to be doing something productive or achieving specific measurable goals. Have you ever sincerely wondered why the universe created and allows the existence of objects capable of such absolute and transcendent patience? Maybe it's its natural way of ensuring that some precious things are never completely forgotten, that some fundamental memories persist beyond any time measure we can imagine or comprehend. White dwarfs show us that deep time is not an enemy to be defeated or a limitation to be overcome, but rather a patient ally, a gentle sculptor, a silent preserver that works on scales that transcend any human urgency. Let's take one last temporal journey together, a speculative trip to the most distant future that modern science can imagine with some confidence. It's a journey that will take us to an almost unrecognizable universe, transformed beyond any resemblance to the young and energetic cosmos we know today, where white dwarfs will become the last melancholic protagonists of a cosmic story slowly reaching its end. Imagine a universe 100 trillion years old, an age so vast that our current 13.8 billion-year-old universe would seem, in comparison, like the first seconds of a very long day. All common main sequence stars have long since completely extinguished. The majestic galaxies we see today have dispersed, their stellar components scattered by the relentless accelerated expansion of space-time itself. The universe has become a predominantly cold, dark, almost completely empty place. Almost, but not totally. Because in this deep and apparently infinite cosmic darkness, white dwarfs will still be present, floating silently through the void. No longer shining visibly like recognizable stars, but existing as black dwarfs, completely invisible objects, cold to near absolute zero, but still physically present and detectable through their subtle gravitational effects. They will be like elegant cosmic ghosts, crystallized and preserved memories of a cosmic golden era, when the universe was young, hot, and incredibly luminous. It's a profoundly melancholic vision, but also extraordinarily poetic. These silent and invisible objects will be the last direct physical witnesses of a cosmic golden age. When stars were born and died regularly, when rocky planets formed in complex solar systems, when life perhaps flourished and evolved on millions or billions of worlds scattered throughout the cosmos. Have you ever walked contemplatively through an abandoned historic city? There's something simultaneously touching and inspiring about observing architectural structures that once housed vibrant human life, that once were the scene of personal stories, family dramas, celebrations, and tragedies, now silent and empty but still preserving echoes of their former grandeur. The future universe dominated by black dwarfs will be conceptually similar, an abandoned cosmic metropolis, but where the fundamental buildings persist for periods of time that make eternity a familiar concept, preserving the architectural memory of epochs of activity and life. But even in this apparently final future darkness, fascinating physical processes will still be occurring on unimaginable timescales. Black dwarfs, through extremely rare and statistically inevitable gravitational interactions, will occasionally collide with each other after periods of orbital approach that last longer than the entire current universe. When these extremely rare collisions finally happen, they could form stellar mass black holes or even briefly reignite as temporary stars, creating sudden flashes of light in a universe that hasn't seen new stars born for trillions of years. Imagine the profound cosmic poetry of this situation. Two black dwarfs, floating silently through empty space for trillions and trillions of years, following orbits that gradually bring them closer in a gravitational dance that lasts millions of times longer than the current age of the universe, until they finally touch and, for a brief cosmic moment, make the entire universe nostalgically remember what it was like to have active light. These collision events will be so extraordinarily rare that the average interval between them will be measured in periods of time for which our human language simply doesn't possess adequate words. But they will inevitably happen, adding occasional dramatic punctuation to the silent story of the aged cosmos. And after? Well, even the black holes formed by these collisions will eventually evaporate through Hawking radiation, a quantum process by which even these final cosmic devours are not truly eternal. In an even more inconceivable future, they too will whisper their final goodbyes to the universe. But this leads us to periods of time so vast that our language and human concepts simply cannot adequately deal with them. We're talking about timescales on the order of 10, 100 years or much more, numbers that need specialized scientific notation just to be written in a comprehensible form. It's as if the universe had invented a practical form of eternity that isn't technically eternal, but that is so astonishingly long that it might as well be indistinguishable from true eternity for any known observer or physical process. A practical eternity, a persistence that transcends any time measure we can really understand or relate to our experience, but that still operates within the known laws of physics. And in this speculative journey through cosmic deep time, white dwarfs emerge as the silent and persistent heroines of the complete universal history. They are the patient guardians of memory, the dedicated preservers of history, the witnesses that persist when everything else has already transformed or disappeared eras unimaginable ago. There's something profoundly comforting and even spiritually nourishing about this scientific idea that even when everything seems to have definitively ended, when the universe seems to have reached its natural end, there will still exist silent whispers of the greatness that once existed, crystallized memories that preserve the dignity and beauty of epochs that will never return. And so we arrive at the end of our contemplative journey through the silent cosmos. Or would it be more precise and poetic to say that we arrive at the beginning of a contemplation that can and should last a lifetime? Because there's something profoundly transformative about white dwarfs and their eternal silence that naturally invites continuous reflection, cosmic meditation, philosophical questioning that has no definite end. Do you clearly remember how we began our intimate conversation? Talking about silence, not the mere mechanical absence of sound, but the positive presence of something much deeper, more meaningful, more nourishing to the soul. Now, after exploring together the most intimate secrets of silent stellar deaths, this fundamental concept has gained rich layers of meaning and understanding that simply didn't exist before we embarked on this journey. The silence of white dwarfs is not an existential void. It's a plenum, a concentrated fullness. It's loaded with cosmic history, crystallized memory, patience that transcends time, transformation that preserves essence while changing form. It's a silence that speaks eloquently about metamorphosis, about persistence, about the profound beauty that can exist in absolute quietude. When we look at the night sky now, tonight, tomorrow, or on any future night, our perspective will be fundamentally transformed. Among the visible stars that twinkle cheerfully, we now know that trillions of silent objects exist, white dwarfs cooling patiently, carrying the intimate memories of cosmic epochs long forgotten. It's like discovering that what we thought was a completely silent library is actually full of invisible whispers, of conversations and frequencies our ears can't directly detect, of stories being told in languages we're only beginning to learn. Each twinkling point of light we can see may have a silent destiny waiting patiently for it in a distant future. Our own star, the sun that warms us every morning, will one day go through this same elegant transformation. In approximately 5 billion years, it will become a majestic red giant, then a colorful planetary nebula, and finally a white dwarf that will cool silently for trillions of years. It's a perspective that might initially seem melancholic or even frightening, but I prefer to see it as profoundly comforting and inspiring. There's something extraordinarily beautiful in the idea that not everything needs to end in cosmic violence, that some transformations can simply transition smoothly to a different form of existence, more refined, more essential, more lasting? White dwarfs teach us about the cosmic dignity of silent transformation. They demonstrate that it's possible to age with universal grace, that it's possible to become something fundamentally new without losing the precious essence of what came before. They also teach us deep lessons about patience, not ordinary human patience measured in years or decades of life, but transcendent cosmic patience, measured in geological eras and universal epochs. It's a lesson about perspective, about how our natural human urgency is just a small musical note in a much longer, more complex and more beautiful symphony. And perhaps, most important of all, they teach us about the universal language of silence. In an increasingly noisy world where everyone seems to be competing to shout louder to be heard, where noise has become almost environmental pollution, white dwarfs whisper their eternal wisdom. Not everything that is profoundly important needs to be loud. Not everything that is truly significant needs to be obvious or dramatic. Have you ever noticed how the most meaningful and transformative conversations sometimes happen in the lowest and most intimate tones? How the most touching and memorable moments are often the most silent and contemplative? White dwarfs are the cosmic version of this universal human truth. They constantly remind us that the universe has abundant space for both grandiose and dramatic spectacles and for discreet and contemplative beauties. That there's equal value both in the supernova that illuminates an entire galaxy in a dramatic flash and in the white dwarf that whispers its story patiently through trillions of years of silent existence. And now, as our contemplative journey together reaches its natural end, I want to express my sincere gratitude for your company in this cosmic exploration. You've been a wonderful and attentive traveling companion, willing to venture with me through deep time and eternal silences, through concepts that challenge our human understanding and invite us to expand our perspective on what it means to exist in such a vast and ancient universe. When you look at the stars tonight, or tomorrow night, or on any future night when you need perspective and tranquility, remember fondly the invisible white dwarfs floating silently among the visible lights. Remember that the cosmos is full of silent whispers, crystallized memories, infinite patience waiting to be discovered and appreciated. And maybe, just maybe, you can find and incorporate a bit of this transcendent cosmic serenity into your own daily life. A bit of this extraordinary capacity to exist fully without needing to shout to be noticed, to communicate through authentic presence, to find profound beauty in silent and gradual transformation. The universe is incomprehensibly vast and ancient, full of mysteries we don't yet completely understand and that we may never come to fully comprehend. But one truth we know with scientific certainty: it created these extraordinary creatures, white dwarfs, that teach us that not all greatness needs to be seen to be real, not all beauty needs to be obvious to be touching, not all communication needs to be heard to be deeply meaningful. Sometimes, frequently, silence is the most eloquent, most lasting, and most universal of all possible languages. May this contemplation continue echoing softly in your consciousness, like the residual glow of a white dwarf, warming your thoughts through the personal eras yet to come. And now, in the contemplative quietude that naturally follows our journey through the silent cosmos, I leave you with a question to carry with you through time. If the universe developed two fundamentally different ways of dying the spectacular and temporary shout of supernovas and the eternal and patient whisper of white dwarfs, what does this teach us about the equally valid different ways of existing, of communicating, of leaving our personal mark on the incomprehensible vastness of time and space, and about how silence too can perhaps be the most eloquent and lasting language of all?